Hi guys, let's move ahead in chemical thermodynamics. Now let's talk about Gibbs energy. Now we all are aware why did Gibbs energy come into picture. Why? Because in our earlier video we saw that we started with entropy of system and then we ended up with entropy of system total, which included even the surrounding. And why was that? That was because in case of steam to conversion to water, entropy, that is disorder, del S was negative. In spite of that, it happened. Alright, so that itself proved that even if del S is negative of system, the process goes on, the process works. So came in del S total, and del S total included surrounding. So as per Gibbs, it is the system we are concerned with, not with surrounding. Alright, so he introduced new term called as Gibbs energy, which formulated this way: H minus T S of system. Alright, why did this get into picture? Because we are more concerned with system than surrounding and system total. Alright, fine. Another important aspect that you've got to always keep in mind is H, T, S and G are state functions. Now these all come into MCQs. Earlier we had seen P, V, N and T, whereas its pressure, volume, temperature and number of moles were also state functions. So you got now 8. You got 8 state functions now. Alright, and what is state functions? State functions is that which talks about state of matter. Alright, state of process. Alright, okay. Now del G obviously is change in Gibbs energy. Del G, change in Gibbs energy is del G is equal to del H, difference in enthalpy, minus T, del S, difference in entropy of system. Got it? Okay. These are all the parameters that you have got to keep in mind always. Del G, when it's greater than 0, the process is non-spontaneous. Mind you, when del S was greater than 0, that is positive, it was spontaneous. Alright. Whereas del G, when it's less than 0, that is negative, the process is spontaneous. Mind you, del S less than 0, that is negative, it was non-spontaneous. Del G is equal to 0, process is in equilibrium. Alright, and the same was also with del S is equal to 0, the process in equilibrium. Alright, so these are the things that you have got to keep in mind. Alright, because there would be lots of questions where it would be asked by varying del G and del S, which I would pick up later. Alright, okay, so these are the things that we have got to keep in mind. And now let's progress ahead into equilibrium. What happens at equilibrium? How does the formula get new format when del G is equal to 0 or when the process is in equilibrium? Okay, at equilibrium del G is equal to 0. So we check out this becomes 0. So it becomes del H minus T del S. Alright, so T, if I take this side and this remains here, so T is equal to del H upon del S. Alright, so this is yet another formula, alright, which you have got to keep in mind. Now suppose if the reaction occurs, if A plus B gives you capital C, capital D with stoichiometry small a, small b, small c, small d, then for this chemical reaction del G would be equal to del G0 plus RT ln QC formula. QC, I guess you are aware about QC. QC, suppose if we have a reaction going on, this is say percentage conversion, and this is a reaction, alright, progress of reaction. So the reaction, if it is this sort of reaction is progressing and it reaches an equilibrium. So what do you understand? So this is say Kc, equilibrium constant. So when Qc, that is reaction quotient. Now if reaction quotient is less than Kc, that means the reaction has yet to move forward to get into equilibrium. If QC is equal to Kc, that means reaction has already reached Kc, equilibrium. Alright, and if Qc is greater than Kc, then reaction has moved forward, it would be coming backward to get into equilibrium. Okay, that was what was reaction quotient. Alright, so del G is equal to del G0 plus RT ln C. Now del G, we are talking, whenever we are dealing with chemical thermodynamics, we are concerned in gaseous state. So instead of Qc, the concentration, we would talk in terms of pressure of C with its power as stoichiometry, same way PD, D, PAP. So this is product of pressure of product divided by product of pressure of reactant. Alright, so that's what it is. So that's the formula in terms of pressure. Now at equilibrium, as I mentioned, Qc is equal to Kc. So Qc is equal to Kc, and that's all. Right now we are talking in terms of thermodynamics, chemical thermodynamics. So we would be concerned with pressure. So Kc would be equal to Kp. Alright, so and del G. So let's analyze this equation. Alright, now this becomes Kc. Alright, this becomes Kc, and at equilibrium we know del G is 0. At equilibrium del G is 0. So this becomes 0. Del G remains as it is, and minus RT ln Kc instead of Qc, because it is in equilibrium. So is equal to Kc. Now so if I take it in terms of del G, I am taking this the other side, so it becomes minus RT ln Kc. But I want to get it in terms of log to the base 10. So I've got to multiply 2.303 log to the base 10 to convert ln to log to the base 10, and I had explained in my other video log 10, why do we convert ln to log 10, so that we can see the logbook. Similarly here also, if we are taking it in terms of Kp instead of Kc, if we are taking it as Kp, then this is what happens. Alright, so it is minus 2.303 RT ln log to the base 10 Kp. Alright, so this is what is all about chemical thermodynamics, as it's an important chapter, so please study it well. Alright.